We're happy to invite Professor Nestor to give us today's talk. And Professor Tan Xinxin will be the chairman.
Yes, thanks. And Professor Nestor Ryszard got his PhD degree in 1987 in the Copenhagen University, and after that he got the tenured position there. And from 2005 to 2020, he is a professor in the Mathematics Institute of Copenhagen University, and now he is with BIMSA. He is interested in non-commutative geometry in the widest sense, including system algebra picture of the standard model, non-commutative properties, applications to the invariance of three manifolds, and TQFT, current K-theory and KK theory, and some index theory in both analytic and formal algebraic context theory with application to analysis, and the homological algebra, deformation theory, and algebraic K theory, something like that. So let's welcome his talk.
Thank you. Thank you for invitation to give a talk here, and thank you for introduction. So I decided to talk, well, everybody here heard about quantum groups. Not everybody present heard about this version of quantum groups that I'm talking about. That's why I kind of decided to talk at the, doesn't work, does it? Does? Okay, good. That's why I decided to talk about, well, C-star type version of quantum groups. So I will spend 3 minutes to explain the word C-star, okay? But it's not really important in some sense. So everybody here knows what that is, right? Continuous functions on the topological space. Well, X should be locally compact in general, so we would take functions vanishing at infinity. And everybody knows about the norm. There's this supremum norm, L infinity norm of functions. So, and there's a star operation, which is just complex conjugation. Takes function and takes its complex conjugation. So, C-star algebra. So it's basically non-commutative version of topological space. Of course, non-commutative version of topological space. If you remember Grothendieck from 1967, he replaced spaces by functions of spaces. So we forget the space and we think just about the algebra. So we have this algebra and it has a norm corresponding to this kind of norm and it has this adjoint operation. X goes to X star. And there are some identities satisfied, very straightforward identities. Actually, let me write, it's the only one really you need. Norm X star X is norm X squared. So once you have this identity, automatically this becomes algebra of operators on some Hilbert space and closed in this norm. So it always something like A sits in some B of H. So H is a Hilbert space, bounded operators are Hilbert space, and A is a subalgebra. The star operations were joint, and the norm is the norm induced from here. The one you always know is this one, right? You know that one. So that has a complex conjugation, and we know that identity. Z conjugate times Z is the same as absolute value of Z squared. Good. So I'm going to forget, at least for a while, those, and I will talk about those. Okay, so just non-commutative version of functions. And then quantum groups. So it's kind of transition from groups to quantum groups. And I will keep just the easiest case the compact quantum groups. Like compact groups, there are compact quantum groups. And well, I did write down a definition. So, as I said, I don't have space, I just have the algebra. Okay? So, my compact quantum group is just an algebra, unital, you think of these as, well, example, functions on the compact space, on the compact group. So this is an algebra and has coproduct. So this map from C of G to C of G tensor C of G, which satisfies, well, standard coassociativity and satisfies this non-degeneracy condition. So this is coassociativity. So this corresponds to a convolution on the functions on the group. That's translating convolution of the functions of the group into the dual object. I'll tell something about the duality in a moment. These conditions, so they are kind of non-degeneracy conditions. They really say that G has the antipode. They imply that G has an antipode. Like for compact group, there is an inverse of group element. That's equivalent statement. And whenever you see this tensor product sign, it's completed tensor product. So we live in the universe of topological algebras, C-star algebras. So if we write tensor product of topological algebras, it's supposed to be topological algebra, right? And there is always, for these C-star algebras, there is always a minimal completion of this tensor product coming from representations. So with these two conditions, statements, there is a dual of it. So there's a notion of dual of C of G, you'll see it in a minute, which is called the discrete quantum group, like Pontryagin dual of compact abelian group is a discrete group, right? There is a reason for the name. And then again, these quantum groups, the way I write it, it's functions on the group and coproduct. So the dual one will be functions on the dual group and dual coproduct. And this, then the duality relation between this one and this one is, so these are functions on G, the C0 G hat. You could think of it as C-star algebra of G. So dual of a product on the group is convolution on the functions of the group. So dual functions is convolutional algebra. Now, since it's unital compact, one can prove that there exists a hard state. So everybody knows that local compact group has invariant measure, unique up to a constant invariant measure. You can prove the same thing in this compact case. There is this unique invariant measure, normalized, which is a state. So linear function on C of G, linear function on C of G, and it's invariant. So invariance, I just rewrote invariance here. So if you write down what it means that Haar measure is invariant in terms of functions on the group, this is precisely what you get. So there's nothing mysterious, just follow Grothendieck, translate what's happening on space to what's happening on the functions on the space. Okay? We can assume that Haar state is faithful. It's not automatic. Now, given the state, I can construct a Hilbert space. So I wrote L2 of C of G, comma H of G. If you think of G as a group, really group, then this will be L2 space on G with respect to the corresponding Haar measure. But there's this general construction which starts with a C-star algebra and the state, and produces a Hilbert space, which is basically the same construction as you know when you construct L2 with respect to some measure. Literally the same formulas. So that's called GNS representation, L for left multiplication. So it's a GNS representation associated to this Haar state. So there is a left regular representation. There is also right regular representation, just like for groups. Since this thing gives antipode, I can find a right regular representation, so kind of multiplication from the right. Then the dual group has again invariant, left invariant Haar, this time weight, not necessarily a state weight. So if you think about unique, so S1 and the dual Z. So S1 has normalized Haar measure. Z has discrete invariant measure, which is not normalized. That's precisely what's happening here in general. But the two L2 spaces, the one constructed from G and the one constructed from G hat, are isomorphic. That's Plancherel formula in this context, still holds. When just like H carries left and right representations of C of G, it carries left and right representations of C star G. And again, lambda rho and ln are interval equivalent because we have a conjugation. We can invert elements. Picture. And the picture I like. So you have a Hilbert space, which is L2 of whatever it is. Whether you can think of it as L2 of a group or group dual, then group C star algebra, X from both sides, there's left regular representation, right regular representation, and group algebra, so functions on the group, again, X from left and from right. So these two commute, those two together generate compact operators, those two together generate compact operators. So basically the statement is that if you take multiplication operator times convolution operator, these things generate compact operators, these products. So I wrote down examples again, so it was talking. So G is really a compact group, just standard compact group. C of G are just functions on the group, coproduct. So delta F at G comma H is F of G times H. I hope you've seen it. And the dual compact group is C star of G. So group C star algebra. Discrete group is not compact, but dual of discrete is compact. So dual of a discrete group. So here the functions on the group is actually the group algebra, reduced because it can be a lot of different C star completions of the group algebra. So that's the smallest one. And the coproduct is the standard one, delta gamma is gamma tensor gamma. And when the dual to C of G is C0 gamma. C of G is C star reduced gamma, C of G hat is C0 gamma. So it's useful to have these two examples in mind. Standard compact group, it's just functions on the group. Dual of a discrete group, group C star algebra. So already highly non-commutative. So functions can be pretty non-commutative here. Okay, groups have representations, quantum groups have representations. Okay, so I'm not going to surprise anybody if I say that there are representations of such a quantum group on the Hilbert space. So I wrote definitions. So there's a unitary in, so compact operators on our Hilbert space, tensor functions on G. M stands for multipliers. Since I want a unitary, I need an algebra with unit. If I take compact operators and tensor with anything, I will never have a unit. So I'm looking things which multiply K tensor C. There's a unit there. So I can ask for unitary operators in there. And this identity corresponds to, well, the representation. Well, let me write U, right? So that you know what's going on. So if I've got representation of a group, well, U of some Hilbert space, then this unitary just is a multiplication. So it takes on L2 of G tensor H, and just pointwise multiplication by this function of G with values operators here. Okay, so that's U. That's this one. And well, this condition here just says that this is a homomorphism from group to unitary group of a Hilbert space. Just straightforward translation. So all the theory works, so you can define intertwiners, you can define irreducible representations, just take standard definitions and express it in terms of functions on the group. Nothing else happens. There is one thing which one never thinks of when one studies group theory. So the point is that, well, there is a regular representation of such a G. So we know what left regular representation of group is. Quantum group has a left regular representation, and in these terms, it's some operator, unitary operator. Well, this term times H will be just L2 of G. Then this acts also in L2 of G. So it will be some unitary operator acting on L2 of L2 of G tensor L2 of G. Actually, this operator has this form, sits in the tensor product. The left leg is in the group C star algebra, right leg is in functions of the group, has the property that coproduct on X is really defined by conjugation with V star, where X sits in the dual on C star G. So coproduct is given by conjugation with V. V is multiplicative. So a lot of people here heard about multiplicative unitaries in this stuff, right? So V is a multiplicative unitary, and this is the same as saying that this is a representation, literally. Okay, that's all it means, multiplicative. Now, this has a special property that, let's think a bit. So this is a unitary which sits in the tensor product of algebras. So it sits, so suppose I take a linear functional on the first component and evaluate linear function on first component. So I get something like this, right? When I get operator, then I get something in here. I will say what the star is in a second, right? So, but I get lots and lots of elements in C of G, and actually these elements are together norm dense in C of G. So C of G's continuous functions can be recovered from this regular representation, from unitary defining regular representation. If I take my functional and hit the second leg, so hit this one, then I get an element here. So these things, all of them sit in C star G, and again, they form a norm dense, actually subset. It's not really subalgebra. You have to complete to get subalgebra. And actually the completion gives C star G. This lower star means that my functionals are supposed to be nice. Just say vector states or something like this. So normal functionals on B of H. But thinking about vector states is good enough. And since I already said the word Pontryagin duality, well, this actually gives Pontryagin duality. So given element in C of G, an element of C star G of this type. So element in C of G, which is something coming from omega acting on C star G and mu acting on C of G. So the tensor products, well-defined map to omega tensor mu evaluated on V. So remember, V is a unitary in this tensor product, in multiplies of this tensor product, right? So this is linear functional on this tensor product, so I can evaluate and get a number. So it gives actually a pairing from C of G and C star G, well, two numbers. It's non-degenerate, densely defined, and that's Pontryagin duality, the one that you know. So this is the character map, or character table on abelian groups. That's what this one is. And then I had, so we defined coproduct on C star G. It also defines coproduct on the dual, C of G, or C0 G hat. So it also defines a coproduct on the dual. So this regular representation carries all the information you can imagine. Just as it is. Well, subject of this talk is really something about G C star algebras, something about the twisted actions of compact quantum groups on C star algebras. So I had to say what it means group acting on algebra. We know what it means a group acts on algebra by automorphisms. Again, translate into functions on the group with values in A. So if I translate it, so yeah, let's say this one, right? So given element A, I can write delta A, which is a function on the group with values in A. So action of G on A is such a map from A to A tensor C star G. And again, it has satisfied associativity, which means that delta is a homomorph, which means that the action G is a star homomorphism. So preserves the structure of A. And there is this non-degeneracy condition, similar to the previous one. So for a compact group, classical compact group, that's the picture. If my compact group is the dual of a discrete group, then this is the picture. It just means that I have gamma grading on my algebra A. Sorry, going the wrong way. Okay, it's kind of projective representation. That's kind of main subject. So, well, we know what projective representations of groups are, right? So we know now what representation of quantum groups are. Well, the definition is actually not quite the same, not the representation, projective representation up to homomorphism. We think differently. Given a projective representation of a group, it gives a representation of a group as automorphisms of B of H. So to each element G, we associate add of G acting on B of H. So it's really a map from functions of the group to operators so it's an action of G on B of H. So we already had one notion. So it was a map from A to A tensor C of G, right? Well, we know that projective representations come from some cocycles, typically Borel cocycles. It's very seldom that we can write down continuous cocycles. So instead of functions, I will get L infinity of G. So just one comment. I defined quantum group using continuous function, using C of G, so C star algebra, C of G and C of G hat, C of G and coproduct. I could just as well think about L infinity of G. So for classical group, that's just L infinity of a group with respect to hard measure. For dual of discrete group, it will be the group for Neumann algebra. So you take the group, you let it take regular representation, and take weak closure. So the largest thing you can construct out of it. Remember, C star G was norm closure of regular representation. L of G, so for Neumann algebra associated to G, or so I wrote L infinity of G, this will be the weak closure of C of G. And the action will, projective representation will be action of L infinity on B of H. The action is continuous, so a cocycle is continuous if it actually restricts to action of C of G on K of H. Right? So instead of having a map from B of H to B of H tensor L infinity, we get map from K of H to K of H tensor C of G. Then it's continuous. Now there's the terminology that I'm not responsible for, but unfortunately it is there. It's called cleft if it's implemented by unitary. Right, this coaction, so this representation. So if there is a unitary in here, such that the delta of A, so this delta, you take A tensor 1, in A tensor 1, so AX on B of H. So A tensor 1, it's in here, and conjugate by this unitary. I would say unitarily implementable. Basically, what it says is that for a group case, it just says that any automorphism of B of H is inner. So in the case of a group, any such action is pointwise inner. So the representation of a group as automorphism of B of H, every automorphism of B of H is given by conjugation with a unitary. So I've got a map from group to unitaries. It's not homomorphism, but it's homomorphism up to a scalar. So classically, this is automatic consequence of the fact that we have automorphism of B of H. For quantum groups, it's not true in general. And this cleft really means the following. So we have this delta, this action of L infinity of G on B of H. We also have another map from B of H here. Let's take B of H and tensor 1, just tensored by 1. And being cleft just means that these two star homomorphisms, so these two maps of C star algebras, are unitarily equivalent. So there's unitary acting on this one, which maps one map, one embedding to another. So we know that every time I've got an action of classical group on B of H, it comes from some projective representation of the group. Well, in quantum world, it's only true for compact quantum groups. So every projective of compact quantum group is actually cleft. So there is such a unitary. It's not true when it's not compact. It's very easy to find examples of local compact quantum groups when this is not true. Well, I already said the word cocycles, so projective representations correspond to cocycles. Same thing here. So given quantum group, we can write down a 2 cocycle. That's a unitary infinity tensor infinity. So it's a function of 2 variables on the group, right? And it satisfies a condition. So being 2 cocycle, that's the condition. The standard condition, if you translate 2 cocycle from functions from what's happening on group elements to what's happening on functions on the group, you get this. Right? There's nothing serious about that one. And cocycle is continuous, well, if it's a continuous function of 2 variables. Right? So it sits in this C-star algebra. And then there is equivalence notion of cocycles. As usual, the equivalent, if there is some kind of intertwiner between omega 1 and omega 2 composed with coaction. That standard notion of equivalence of 2 cocycles for groups. By the way, there are no standard notions of 3 cocycles and such. That becomes different story. Okay, but 1 cocycles, 2 cocycles for groups, quantum groups, work perfectly. Okay, so we have this set of quantum groups, set of 2 cocycles, and we have equivalence. There is no products of these 2 cocycles. Okay. Okay, before I do that, maybe I should comment one thing. So I already started talking about quantum groups acting on C-star algebras. So C-star algebras with action of a quantum group. This is not a tensor category. You cannot, well, if you just given 2 C-star algebras the action of a group, classical group, you can write down tensor action on tensor product. Once a quantum group, so once group dual is non-commutative, this does not make sense. Okay, so C-star algebras with action of a quantum group do not form tensor category. For that matter, it does not have to be C-star algebras. Also, as algebra, it doesn't matter how algebraically you work. The tensor product doesn't work. There is a way to avoid it, but it's a different one. Now, given one of its projective representations implemented by a unitary, well, classically, given projective representation, there is a cocycle. Same thing here. So, given the representation implemented by a unitary, so it has to be this cleft one. Then there is always a 2 cocycle, such that representation, so U was supposed to be a representation. If it was representation, then we would have these things equal. Well, they are not, there's this correction here. So we have an omega representation. In particular, if I've got this fundamental unitary of G, remember this is this regular representation of G, which is given by a unitary, then omega tensor V is one of these omega representations, satisfies one of these conditions. That's consequence of this one. Okay, and well, since V is regular representation, this will be omega twisted regular representation, and the omega twisted group C-star algebra is just given by this formula. Remember, we saw before that taking, for example, from identity tensor phi on V without omega produce group C-star algebra. That was this special property. If I put in omega V instead of V, I get what I would call twisted group C-star algebra. So if you are completely algebraic twisted group ring, take a 2 cocycle on the group, you can write down twisted group ring. That's what it is. Okay, how far my time was? Okay. Well, regularity result is just stated, so projective representations for compact groups. So, given two cocycle on compact quantum group, I should say, have said compact. Well, G admits continuous omega representation. So the cocycle is continuous. G admits a finite dimensional omega representation, like compact groups, compact quantum groups also admit be given by lots of finite dimensional representations. So this B of H that I wrote will be finite matrices somewhere. Okay, and the third condition: every irreducible representation is finite dimensional. So these three conditions are equivalent, and then you would call omega of finite type. And now, you remember that I could use omega to twist representation. I can use omega to twist the coproduct. So that add means conjugation. If I use omega to twist coproduct, well, omega lives in L infinity tensor L infinity. So it's a map from L infinity to L infinity tensor L infinity. This bar here is that to remind ourselves that this is completed tensor product. Okay, and well, in general, we get a new locally compact quantum group structure. Not compact, right? Sorry? No, G is compact. Doesn't matter, G is compact. It doesn't matter. Actually, it's stronger. So this is a locally compact quantum group. G is compact. But still, in general, this is locally compact. And this is compact if and only if omega is finite type. If and only if omega is continuous. If omega is not continuous, this is not compact. So if you take a compact group and write down some extension using a Borel-2 cocycle, you get a locally compact group. You will not get compact group. You know that you will get a local compact group because you get a group with some measurable structure. So Mackey's theorem tells you that this is some kind of local compact group, but it will not be compact. And that's the analog here. Okay, I wrote this slide, and then I said, okay, I decided to leave it here. If you know what it is, look at it. If you don't know, don't look at it. It's a definition, right? So this bit is important. So what I'm going to do now, so I'm really thinking about assembly map from equivalent K-theory to K-theory. That's something which is all over. In topology, you have no conjecture, you have Borel conjecture, Farrell-Jones conjectures. In analysis, you have Baum-Connes conjecture. So this appears all over this assembly map. And I need, well, to formulate, I need some notion. So the point is that there is some kind of bivariant functor from C-star algebras to C-star algebras. So it's kind of homotopy type C-star algebra map from A to B. It's not really a map. Actually, to the contrary, it's kind of it's kind of Hilbert space with B as scalars and representation of A, and this Hilbert space will be as scalars, and there are some conditions satisfied, some regularity conditions. I wrote it up. But the main point is that equivalence classes of this thing form an abelian group. So there is this abelian group, KKGAB. G is a, well, locally compact quantum group in general. Or it can be something associated to some groupoid or some relation, or to group. Or actually tensor category for that matter is just as good. Okay, so you can construct this object. Now, the main property of it, first of all, it's an abelian group, but there is an associated product, it's called Kasparov, due to Kasparov. KKAB cross KKBC to KKAC. That's why it's useful, actually. But as the result, I can think about category of these GC star algebras, so algebras where action of G, call it KG, where morphisms are given by this KKAB. This product here gives me composition of morphisms, and on top of it, it is a triangulated category. So it has two structures. It has triangulated category has two properties. It has a shift, right? Well, the shift is a suspension. So tensoring with C0R, or thinking of functions from C0R to A. That's the shift. And exact triangles are given by, well, extensions. I'm not going to use more time of it. But it's very easy to write. It's not so difficult to prove that this gives a triangulated category. But once you have that, you can use homological algebra. And, well, part of it shows up here, right? So I said that there is something here that I'm interested in, especially this assembly map. So let's see what it looks like a bit. So, and I'm going to make life easier for this slide. So I'm going to say that gamma is just a discrete group. Okay? Just a discrete group. And the assembly map, so the gamma itself is a discrete group, not the dual. So now I'm the universe of locally compact groups, quantum groups or groups. But let's look what's happening. So actually I want K-theory of this cross product. So gamma with A, so gamma A with twisted by gamma with a cross product, and there's a regular representation which gives C-star algebra. So we want K-theory of this. If A is trivial, we just want K-theory of group C-star algebra, which controls harmonic analysis on L2 of a group. Okay, if harmonic analysis on L2 of a group is the same as a study of group C-star algebra. So for A trivial, it's just group C-star algebra. But it's in the KK category, so let's figure out this one. So I want K-theory of this. Well, I can construct some elements in K-theory of this using my K factor as follows. So let's suppose that H is some open compact subgroup, so it is torsion subgroup of gamma. Okay, so say gamma is discrete and H is torsion subgroup. Okay, now I can look about, remember this KK, I can think about this KKH C comma A, where C is just scalars with trivial action. So it's an old result that this is the same as K-theory of A cross H. This is one of nice properties of this KKH, but if you stick C here, I get K-theory of a cross product in the other hand. So that's the same as K-theory of A cross H. On the other hand, I can do induction. I can use from H to gamma, and things work. So by induction works perfectly on this KK factors. So I can induce from CA to induction from H to gamma A. So induction from H to gamma C, it just functions on gamma mod H. Just C0 gamma mod H. So this commutative algebra, if gamma is classical, right? Well, I can go from this equivalent KK, I can go to cross product. So instead of thinking of equivariance, just throw in this gamma to this, add this gamma to these algebras. So I'm here, and then now I can go here. Now, this map is as follows. So if I have, remember I had the product, I had this product on KK. So if I've got something here, and if A is equal to scalars, when AC, it's K-theory, I can throw it in, and I get K-theory at this end. Okay? So that's what's happening here. So since H is a torsion subgroup of gamma, this cross product here, anybody who ever saw make an induction procedure and construction of representations would know that this thing is just some same, essentially the same as group C-star algebra of this H. It's one of Mackey's basic theorems. On this context, it's kind of Green theorem. In these terms, it's a Green theorem. That's really Mackey's construction. So from 2 centuries ago, somehow. Okay, so I can use unit. H is finite, so group C star algebra of H is a finite sum of matrices, finite dimensional matrices. So the particular constant 1 is an idempotent inverse, element of K0. So I can plug it in the first place, and I get element here in the cross product. So I get a map from here. Actually, let's think of a map from here to here. So what is assembly? We look at these objects. These inductions from H to gamma are some projective objects in KK gamma. So we look at all these things where, well, what I have here is a projective object, and assemble them. For each one of those, I've got a map here, and then assemble some kind of object out of those, put them together. If I put them together, I will get something what's called gamma equivalent K homology. That's the standard notion from topology. So it's the topological object. Using projective objects, assembling them together, I get gamma equivalent K homology. Okay? And then I've got map from this gamma equivalent K homology to K theory. That's the assembly map. Now, there's one more bit. Is it visible? Yeah, let's look at this. So, assembly map. I want to use it to compute something. So actually, there is this conjecture that says that this assembly map is, from here to here, is actually an isomorphism. It implies all the conjectures you can imagine from topology, analysis, everywhere. It has a bit dubious status, okay? But it's true for a huge amount of groups, okay? Essentially, every group you can put your hands on will satisfy this conjecture. But there's this Gromov principle that something that holds for all discrete groups is either trivial or false. This is not trivial, so that's probably false. Okay, good. So I want to say something about this. Now let's do it in, well, rewrite it somehow with a bit different picture. So we have G, we have our gamma, take its dual. It's quantum groups after all, so I can take dual of a discrete group or any group, quantum group, G. And the gamma was discrete, so G is compact. And now, there is this well-Pontryagin dual between Gabelian groups and their duals and then the biduals. Well, the same thing holds for quantum groups. So, given a gamma algebra A, there will be a cross product, which will be a gamma hat, so G algebra A cross gamma. And this map from here to here is equivalence of categories. So I can go continue, take cross product with G, and I will get back in this category. And the result is Morita equivalent to original object. So this is equivalence of categories. So instead of looking at this, I can look at this cross product here, which remember, this was equivalent in KKG to something finite dimensional. So this here, right? So I go over to G, so to the dual of gamma, and now I'm looking at objects which are, well, essentially finite dimensional algebras. Okay? So dual of gamma is G, compact quantum group, and the torsion for discrete quantum group gamma will be a finite G algebra, finite dimensional G algebra. So just translating from one to the other. Right, so torsion for gamma is finite dimensional algebra with action of a dual G. Now, if T is simple, then we'll call it non-permutation type. It doesn't really matter now, but so there is this functional, these constructions here. There's a lot of, since we work in KK gamma, which is a triangulated category, you can throw homological algebra on it, something with There are different constructions. There's the Adam spectral sequence, things like this. Let's not think about that one. But as the effect, what really needs to be done is, so suppose I pick up a finite-dimensional GeoGebra and look at this functor, so kkg t comma a, and for t torsion finite-dimensional, I need this functor to be continuous in A. So it commutes with direct limits in A. In other words, T is a compact object in kkg. So that's one thing. I need to construct my assembly map, and I also need to compute it. Right? I need for each T and A, I have to be able to compute this one. This helps because once I compute it, I can compute assembly map. So, well, let's make a statement. Okay, let's forget this one. So, if T is finite-dimensional GeoGebra and Cn is separable, so C could be trivial, with trivial G action, then there is an isomorphism from kkg C tensor T comma A. So C here has trivial action. So it comes as kind of just notation. It doesn't play any role, right? So not important. The point is that we can shift T to the other side, A tensor T opposite. Well, shift to the other side, so functoriality is different. That's contravariant and scovariant, so I better flip T to T opposite. And therefore, this cross product, well, I'll take cross product, but with G omega, so twisted G. Okay? So finite-dimensional, think of this way, finite-dimensional GeoGebra, it's particular matrices, finite matrices. So action on finite matrices is always inner, so there's always a cocycle, a continuous cocycle omega here. Okay? And we know that given the continuous cocycle on quantum group, we can twist the quantum group by cocycle. So that's what there's some kind of Pontryagin duality, actually Poincaré duality in this context. It is actually a version of Poincaré duality. So given that one, yes, T is compact object, and on top of it, yes, I can compute this. Because I can compute K-pure of these cross products, typically. That's something which is computable. But remember, this was something like no, I wanted to go back, right? Yeah, this was something like this. So group C star algebra of H. So this kind of object. So easily computable. Okay. So, well, at least some result. So, okay, before I go to that one. So I was talking about Baum-Connes conjecture. So, where was this map? Yeah, this map, right? From equivalent K-theory to K-theory of cross product. So what's the status of this thing? As I said, for any group that you can put your hands on, typically satisfies this. So not all of them, but if gamma is a hyperbolic group or limit of hyperbolic groups, actually the most difficult proof you could think of is when gamma is amenable. It's also true when gamma is amenable, for say R for that matter. Okay, so in most cases it's true. For quantum groups, it becomes much more complicated. So the point is that for classical groups, you can do a number. If you have a classical group, then you know that the category of G algebras is a tensor category. So you can take two G algebras and tensor. So what's happening there is that in this case, you just look at C comma C. You find something in C comma C. Actually, it's from C comma, let's say, C here to C here. So you find an element KK, some kind of KK element which goes from here to here, and then you can tensor with A to change coefficients. So if gamma is classical group, using the fact that it's a tensor category, it reduces to computations for trivial coefficients. It's non-trivial computation, but computation for trivial coefficients. In the case of quantum group, it's not true anymore. So you have to do it for all possible A's at the same time. So you really have to work. So there are not that many cases known when it's true, but when gamma is, say, SUQ2, quantum SUQ, right? System algebraic one, when it's true. When gamma is one of these so duals of liberated permutation groups. So given permutation groups, there is a natural way of constructing associated quantum groups, which is basically doing quantum information theory. Well, what people do in quantum information theory, they look at some permutation groups, make them quantum, and then try to compute something, try to compute some states of them. That's, they don't say it, but that's what they do. So, so for these groups, so it's also true. But in general, there's very little known. But at least we know that there exists kind of assembly map, well-defined assembly map, which requires this one. Sorry, I'm going the wrong way. Last slide. Okay. So was question about compact quantum groups. So compact groups, one thing you know, everybody should know about compact groups is Peter-Weyl theorem. Right, so all representations, irreducible representations of compact groups are finite dimensional, and the corresponding group algebra. So if these are representations of a group, then the group algebra is just direct sum of matrices over representation space. So this is really H tensor H dual. So these are linear maps from H to H. So if H is finite dimensional Hilbert space, so this is just matrices, so endomorphism of H of P, pi. If H is infinite dimensional, then these are actually Hilbert-Schmidt operators on H of pi with L2 norm, right? So one has to be careful with this. But if G is compact, well, we know that all representations are finite dimensional, and group C-star algebra is direct sum of matrices. And if I've got a two cocycle, well, this Peter-Weyl theorem still holds in the sense that, well, the group C-star algebra is a direct sum of the irreducible omega representations. Remember, omega does not have to be continuous. So this G omega does not have to be compact quantum group. But still, this twisted group C-star algebra is direct sum of all representations of twisted representations. And I think example would be in place. Think of Z2, group Z2, and the standard two cocycle on Z2. So group C-star algebra of Z2 is just continuous functions on a two torus, right? There's Pontryagin duality. If I take standard cocycle, then twisted group C-star algebra actually compact operators. There's only one irreducible representation, right? So this can be an infinite dimensional. So this can be quite different from group C-star algebra of G. First example you can think of, okay? So if omega is finite type, then we have actually a compact remember when this twisted G is a compact quantum group, so we can use standard methods, and there's this twisted cross product, so twisted action of G on A, and then there's a dual action. So I think everybody saw this in the abelian case, right? So it's cross product and dual cross product, right? And this double cross product actually does the same thing as in classical case. So this dual cross product washes out the cocycle. So if I take twisted cross product and then dual cross product with dual group, result is algebra tensor compact operators. G and G hat each other wash each other out. Whether there's a twist or not doesn't matter. They all always wash each other out. Well, it has an effect. So, well, that's what I wrote it. It's in the C-star algebras, it's called Packard-Rayburn trick. In physics, I think it's called Slavnov trick, right? Which comes from the 1940 or something. And Mackey used such things as well, right? But okay, different context, different words. Okay, but now let's look what's happening. So I'll start with twisted action, take cross product, dual cross product. Now, this thing here, so now I've got this G hat, cross product with G hat, and there's action of G on that. So I can take invariance on the G action. Well, I don't get, if I took invariance on the G action, I would, in the classical case, I would just, if there was no twist here, I would just get A. Here, I will not get A. I will get A, but with twisted product. So take cross product with twisted cross product with G, dual cross product, and then invariance on the original G action. The result is, as vector space, result is A, but product is different. So you get a, well, quantum algebra, quantum space actually. So holds for not necessarily compact quantum groups, source of the formation of algebras by cocycles on quantum groups. So things like Riefel deformations are actually precisely of this type. So they come from this picture. And I think I will stop. Did I say thank you? No.
Okay, any question?
I have two questions. Please go back to the 3 pages. I guess the main conjecture between the dash line between KK theory and K theory. For the discrete group gamma, how many groups do we know? For example, such as the finite long abelian groups, do we know? I'm not familiar with. I want to know is that do we shall we know the simplest unknown case for the discrete group gamma? Is there a serving article about this isomorphism?
No, so if gamma is finite, it says nothing.
It's trivial.
Yeah, if gamma is finite, it says nothing because, see, this equivalent K homology, this thing, it's really built, so this was go from here to here to here. So this thing, this K homology is built out of these cross products, right? So this group is finite when both sides are the same. The group is finite, right? If you could think about this statement as, so in terms of this homological story, this KK gamma category,
yeah,
you can think of saying that this the fact that the assembly map is an isomorphism just says that if you have an algebra, gamma algebraic, and if this is an isomorphism for all discrete subgroups, sorry, all torsion subgroups of gamma, then it's true for gamma. That's really what it says. Okay, so for Z it says nothing. For one of crystallographic groups, well. So for torsion doesn't say anything, right? But for gamma non-torsion, not finite. So as I said, gamma eminabu, that's probably the strongest result in some sense. Gamma, well, gamma eminabu covers a lot of things, right? So free groups, hyperbolic groups, there are those delta hyperbolic groups, groups acting on cat1 complexes. So a lot, it's known for a lot of groups. in this form. The problem, so there is a weaker conjecture where coefficients are trivial. So just map from gamma equivalent K theory of C, so trivial, to K theory of group C star algebra. That's known for more of these groups. So for example, it's true for SL and, for locally compact semi-simple groups. For locally compact semi-simple groups, this is true, with trivial coefficients, not with arbitrary coefficients. Actually, for any locally compact separable group, without coefficients, it's true. But locally compact, not fine, not total, and not actually also totally disconnected. But problems is discrete groups. Really, the real problem is what's happening there. So, as I said, you can do it. Gamma does not have to be a group or quantum group, can be a groupoid. In the case when gamma is groupoid, there are counterexamples. But that's kind of silly counterexamples which come from the fact that cross product, so this map really factorizes through full, so maximal cross product, not reduced. And things vanish. So the counterexamples are related to
probably a lot of questions should be related to for in classical algebraic topology there is called the Brown representation theory. That means the cohomology theory is representable.
Yes.
There should also homology is also representable. So there you should have, if you're familiar with the G equivalent homotopy theory, there should also representable for those both homology and cohomology. Okay. I ask questions. KK gamma is representable?
No. Oh. KK gamma is not. So this is of K homology is representable.
Okay, thanks.
That's representable, really. But this one, the other side is not. Problem is this R. So this is not does not satisfy excision the first variable as it stands for purely analytic reasons. As soon as gamma is not amenable, the excision fails. Okay, so that's actually why it's so interesting that you have a purely topological object. So that's topological computation, and this is a real analytic object, which is analytic computation. So topology and here representation theory, and they get related to each other.
Any other question?
For what kind of compact quantum group you can compute the two cocycles?
Well, you can write for most of compact quantum groups, you can actually compute the cocycles. You can compute the group of the cocycles. So no, there are typically you can for at least all these matrix compact quantum groups. So SUN or SUQN, for example.
Any other questions? Okay, if there is no more question, let's thank Ryszard again.